So as we already know how to deal with the PCA. Still, we haven't talked anything about the mathematics of PCA, but at least now you know how PCA in general works, isn't it? Yeah. So this is something I explained already. If you have two variables, yeah, and then if we have two categories, we have to find that vector, typically called as a principal component, and then we have to project this data onto that particular vector. And then we have to see whether is there any clear separation, or if there is a clear separation, that means it carries all the information that we need. So that's the meaning of that. So what I'm going to do is, so how to do that, I explained how to reduce the dimension, and the essence of PCA. I talked very briefly about the eigenvectors and eigenvalues. So now we will learn the full technique. Yeah. So what you are going to do is, so as I said before, we're going to, let's say we have some data, something like that, and then we have to find the best eigenvector. Yeah. So this may be here, and then when we project all these values there, so there shouldn't be a clear overlap, and we have to make sure. So this is something, the word which I'm using at the moment is we are projecting the data, but we have to prove that mathematically. Yeah? So mathematically, how to prove that? We have to calculate the variance captured on this particular principal component. Yeah, that's something we will calculate now. Yeah, so how to do how to deploy the PCA if when you have a data something like here. Yeah, so what's this data is about? So what I have here is we have 6 different materials. So these materials are used for hydrogen storage, and then what this material do is, so it can store this material, you can it can go it can sustain high pressure. Yeah, so it can store hydrogen until a pressure of 35 bar. Another material can sustain at 45 bar, sorry, another one 30 bar. So these are some limitations of the materials. And this material you can even store hydrogen until up to 250 bar. So this can handle really high pressure. So this material is really stable to high pressure. And on the other hand, in terms of deliverable capacity, so deliverable capacity is something typically we call it as so if you want to drive a car using hydrogen, so make sure that you have a material that can store hydrogen at this high pressure. But deliverable capacity is something like so how much you store at storage pressure, which is this column, minus how much hydrogen you can actually storage at 5 bar. So the difference will become the deliverable capacity. So to drive the car, the deliverable capacity should be really high, so that you can drive the car at least for say for example 400 kilometers. So what we see here in this table is you have 6 different materials, and they can store hydrogen at different pressure. Some can store at low pressure, some can store at higher pressure. But on the other hand, what we see is something here is very unique. This material, though it's operating at lower pressure, it can deliver really high amount of hydrogen in terms of weight percentage, 5.8, 6.2, 5.4. On the other hand, this material seems like they are highly stable at higher pressure. You can operate this material at higher pressure. Still, the deliverable capacity is still very low, isn't it? The deliverable capacity is really low here. So that's the whole essence of the problem. So what we need to do is, okay, forget the how we are going to store the hydrogen or what type of material it is, but the goal of this video is to explain you how to deploy a principal component analysis and reduce the dimension. So what we have here is you have one variable which is your deliverable capacity, and another one is your operating pressure, and these are the different samples. So these are M1, M2, M3, M4. These are different materials. So you can consider this one as your sample number, maybe 1, 2, 3, sample number 5, and sample number 6. So if you write the data set, so you can write it in a matrix format, isn't it? Yeah. So 5.8, 6.2. So that makes one variable, and another one is that makes another variable. And this column, if for your convenience, we can call it as x1. This column we can, or maybe we can call it even x, and this column we can call it as y for convenience. Okay, so before deploying the principal component analysis to reduce the dimension, what we have to do is you have to tell something about the data itself. Yeah? So what's the size of the data? Size of the data is row multiplied by column. So size of the data is 1, 2, 3, 4, 5, 6. 6 rows multiplied by 2. So that's the size of the data, or the dimension of the data. Yeah? So which means 6 by 2 matrix. So that's not, whenever I ask the size of the matrix, you have to write the row and then the column. Yeah? So that's the rule, mathematical rule that you have to follow. Yeah? So how do you deploy the principal component analysis? So before that, so number of samples. Yeah? Take a note of the number of samples we have. So number of samples we have is 6, and then the number of variables is equal to 2. So these are some numbers that you have to remember. I mean to understand about the data. So if the number of variables is equal to 2, so then according to the rules of PCA, we can get up to 2 principal components. But the main purpose of using PCA is obviously to reduce the dimension, isn't it? Yeah? So we have to find the one main principal component. The main principal component, or PC, or we can call PC1. So that can capture all the variance in the entire data set. So this is what we are going to do now. Yeah? So let's do the PCA. So to do the PCA, the very first step is this is going to be a very long video because there are a lot of calculations involved. So I'm going to do the calculation bit by bit. So let's write the data here. So x is so 5.8, 6.2, 5.4, 1.2, 1.6, and 0.9, and then write the y value 45. So this is the operating pressure, this one, 30, 280, 320, and 250. So we have a 6 by 2 matrix, and now we have to reduce the dimension using the algorithm called principal component analysis. So the very first step in PCA is to get something called as covariance matrix. So I will explain what's that. So this is the first step. So let's call this as step 1 of PCA algorithm, or principal component analysis algorithm. So whether you have two columns or you have 100 columns, whether you have 6 rows or you have n number of rows, these rules will not change. Yeah? So it's going to be the same. So first step is to calculate the covariance matrix. And what's the covariance matrix is? Yeah? So if you have two variables, isn't it? Yeah? So which is x, another one is y. So the covariance matrix will be something that talks about the variance in the data of the ordered pairs. Yeah? So that's the meaning of that. So you have ordered pairs. What do I mean by that? So you have two variables. So the number of ordered pairs will be, so you have two variables. So number of variables is equal to 2. So this means you will have 2 raised to the power 2 number of ordered pairs. So if you have n number of variables, then you will have n raised to the power that many number of ordered pairs. So what do I mean by that? Pairs. So you have x comma y, which mean two variables, so which mean 2 raised to the power 2, which mean 4 ordered pairs. So what do I mean by that? So ordered pairs means you have x comma y. So we can write 4 ordered pairs, isn't it? Yeah? X comma x, x comma y, y comma y, and y comma x. So that makes 4 ordered pairs, isn't it? So now we have to calculate something called as the covariance of these ordered pairs. So let's write that. So we have to calculate the covariance of x comma x, x comma y comma y, and y comma x. So covariance of x comma x, the formula is 1 divided by n minus 1. So here n is the number of samples. So I is equal to 1 to n. So here n, which means we have n number of sample, means we have 6 samples here. So x of I minus x mean into x of I minus x mean. So what's this? X of I means x1, x2, x3, x4, x5, x6. So which is this one? x1, x2, x1, x2, x3, x4, x5, and x6. And this one is y1, y2, y3, y4, y5, y6, and then you can go up to yi and then yn. So that's the meaning of that. So here I ranges from 1 to 6. So I ranges from 1 to 6. So how, and then similarly we can calculate the covariance of x comma y. The formula is same, 1 by n minus 1, summation of I is equal to 1 comma n, here n is equal to 6. So x of I minus x mean multiplied by y of I minus y mean. And similarly for covariance of y comma x will be same like this, same formula, 1 by n minus 1, summation of I is equal to 1, n is equal to 6. So I equal to 1 to n, and y of I minus y mean divided by x of I minus x mean. And you can write covariance of y comma y equal to n minus 1, summation of I is equal to 1, n is equal to 6, and then y of I minus y mean multiplied by y of I minus y mean. So this is something we have to calculate. So covariance of all the ordered pairs. So since we have 2 variables, we will have 4 number of elements. So 2 raised to the power 2, that makes it 4. So we have to incorporate all the elements. We have to compile these values and construct something called as the covariance matrix. The common notation is S. S is nothing but it contains all the covariance of all the ordered pairs. So covariance of x comma x, covariance of x comma y, covariance of y comma x, and then here covariance of y comma y. So this will be, you have 2 rows and then 2 columns, so you will get 2 by 2 matrix as a covariance matrix. So what do I mean by that? So if you start with the 2 variables, the size of your covariance matrix will be 2 by 2. If you start with the 3 variables, let's say you have z, then the size of your covariance matrix will be 3 by 3. If you start with n number of variables, then the size of your covariance matrix will be n comma n. So what do we mean by that? So let's say if you have one more value here, z. So let's that can be an operating temperature, for example. So in that case, your covariance matrix will be covariance of x comma x, covariance of x comma y, and then covariance of x comma z, and here it will be covariance of y comma x, covariance of y comma y, and then covariance of y comma z, and here it will be covariance of z comma x, covariance of z comma y, and then covariance of z comma z. So that will make a 3 by 3 matrix. So 3 by 3 means 3 rows and then 3 columns. So that's how we write the matrix. So rows multiplied by columns. So for our case, we will have a 2 by 2 matrix. So let's calculate, try to complete the step 1, which is to calculate the covariance of your entire data set. So how to do that? So since we already have the the formula, it's easy to calculate x covariance of xx, xy, yx and yy. So let's calculate first the covariance of x comma x. So for to do that, we have to take the so we need to calculate the mean value of x and the mean value of y. Yeah. So which means we have to sum all these values and then divided by number of sample, which is 6, and then that makes x mean. And then you have to sum all these values and then divide by 6 number of samples. 6 is the number of samples that makes that will give the y mean. So let's calculate that. So mean of x, the notation is x mean, so that should be all the values, isn't it? Yeah, which is 5.8 plus 6.2 plus 5.4 plus 1.2 plus 1.6 plus 0.9, so divided by 6. So this should be equal to 21.1 by 6. So that's roughly 3.5167. So I already calculated this value, so that's why I'm writing it here so fast. And then you can do the same. So the mean of y, so this should be, you have to sum all the values and then divide by 6. 6 is the number of samples. No? So let's do that. So that will be 35 plus 45 plus 30 plus 280 plus 320 plus 250 divided by 6. So that should be equal to 160. So this is the mean value of x is equal to 3.5167, and then the mean value of y is equal to 160. So now we have to calculate the covariance of x comma x, covariance of x comma y, covariance of y comma x, and covariance of y comma y. So let's first do this. Let's calculate this x minus x mean and then y minus yi minus y mean. Yes, so let's do that for different materials. So we have m1, m2, m3. So we have different materials, isn't it? We have 6 different materials. So let's calculate x xi minus x mean. So this is, so we have already the mean value. So we have to subtract the mean value from each of these number. 5.8 minus x mean, 6.2 minus x mean, 1.2 minus x mean, and so on. So if you do that, 5.8 minus 3.5167, 6.2 minus 3.5167, 5.4 minus 3.5167, 1.2 minus 3.5167, and do the same for 1.6 minus 3.5167, and then finally 0.9 minus 3.5167. So this should be equal to 2.2833, 2.6833, 1.8833, so 2.3167. This should be equal to this should be minus 1.9167, and then this should be equal to minus 2.6167. So similarly, you have to calculate yi minus y mean. You know? So yi is what? We have it here. No? So 35 minus the mean value. The mean is 160, which is here. So let's do the same. So 35 minus 160, 45 minus 160, 30 minus 160, 280 minus 160, 320 minus 160. Obviously, you have to do a lot of calculations, but so that's how this algorithm works. Yeah, there is no shortcut. So minus 125, this is equal to minus 115, this is equal to minus 130, and this is 120 equal to 160, and finally the last value is 90. So we get x minus x mean, y minus y mean. So this should be enough to get the covariance of all the ordered pairs. Yeah? So let's do that. So let's do the covariance matrix. So the covariance, so let's write the covariance of xx. Covariance of xx is nothing but 1 by n minus 1 summation of I is equal to 1 to n. Here n is equal to 6, no? And then x of I minus x mean into x of I minus x mean. So which mean 1 by 5 n is equal to 6, 6 minus 1. Summation means you have to sum all these values, isn't it? You know? So x minus xi is this one, isn't it? 2.2833 multiplied by 2.2833. You know? So this is 2.2833, this is 2.2833. So which is, we can take the whole square, isn't it? Yeah? So we do that one. So 2.2833 whole square plus 2.6833 whole square plus 1.8833 whole square plus 2.3167 the whole square plus minus 1.1967 the whole square plus this value minus 2.6167 the whole square. Close the bracket. So if you calculate this value, so this should be equal to 1 by 5 multiplied by 31.8483. So that so if you calculate, divide by 5, so you should get 6.3697. So this is nothing but your covariance of x comma x. Yes, really a lot of calculations to be done. So 6.3697. So let's do the calculate it for the covariance of let's do for the covariance of y comma y. The procedure is same, isn't it? Yeah? So 1 by n minus 1 summation of I is equal to 1 to n y of I minus y mean multiplied by y of I minus y mean. So this is, you can write it like 1 by n minus 1 summation of I is equal to 1 to n y of I minus y mean the whole square, isn't it? Yeah? So which means so let's calculate this value. So equal to 1 by 5, so minus 125 the whole square plus minus 115 the whole square plus minus 130 the whole square. So these values are coming from here. Yeah? So we already calculated minus 125, 115, minus 130. So I'm just taking the whole square of this value in order to compute covariance of y comma y. Just implementing the formula. Yeah? No magic is happening here. Plus 160 the whole square plus finally the 90 the whole square. So if you sum all this value, this should be equal to 1 by 5 multiplied by, if you compute all these values, you will get 93850. That should be equal to 18770. So you have to use pen and paper. You have to practice yourself in order to to deal with this type of problem. You know, you cannot just watch a video and then assume that you can solve this type of problem in the final exam. It will be really difficult. better practice in home one time. Just repeat the whatever I'm doing now. Take a pen and paper, just write it yourself, take notes. So that's how you can learn this module. Yeah, so machine learning algorithms, they are not algorithm, it has some mathematics, isn't it? Without knowing mathematics, you cannot deploy any algorithm, any machine learning algorithm. So for this module, we are learning really three important algorithms on a support vector machine, principal component analysis, and deep neural network. All are really, really important and probably the most used algorithm. So that's why we are learning this one. So I'm teaching in general the how the algorithm works. So it can serve anyone, yeah, not only for this module. It can deal almost any type of problem where you think machine learning can be a useful method, yeah, to deal with that problem. So let's see, we already calculated covariance of y comma x, y comma y, and x comma x. So now we have to calculate covariance of x comma y. This should be equal to covariance of y comma x. So why is that? If you look at the formula that way, so covariance of y comma x is 1 minus n minus 1, y of I minus y mean multiplied by x of I minus x mean, and x of I is almost same, isn't it? Yeah? The only thing is I flipped it here. Here you have xi minus x mean and yi minus y mean. So covariance of x comma y, that should be equal to covariance of y comma x. So covariance of so let's calculate the covariance of x comma y. That should be equal to covariance of y comma x. This is equal to 1 minus n1 summation of I is equal to 1 to n x of I minus x mean multiplied by y of I minus y mean. So this is really easy to calculate, isn't it? So equal to 1 by 6 minus 1, and then summation means you have to sum the product of these two. So this value we already calculated, xi minus x mean, yi minus y mean. So we have to just multiply these two, and then we have to sum all the values. So we have to multiply this one multiplied by this plus this one multiplied by this plus this one multiplied by this. So let's do that. So x of I, so 2.2833 multiplied by minus 125 plus 2.6833 multiplied by minus 115 plus 1.833 multiplied by minus 130 plus minus 2.3167 multiplied by 120 plus minus 1.9167 multiplied by 160 plus minus 2.6167 multiplied by 90. So compute this value. So you should get 1 by 5 multiplied by minus 1659. That should be equal to 331.8. So this is covariance of x comma y, and that should be equal to covariance of y comma x. That should be equal to 331.8. So now we have to arrange all the four elements, so composed by the covariance of ordered pairs, into, we have to compile them into the covariance matrix S. So S is nothing but xx xy covariance of yx yy. So we already calculated each of these elements. Now compile them and then construct something called as the covariance matrix S. So S will be equal to, so the covariance of XX, covariance of xx is 6.3697. Covariance of xy is minus 331.8. And covariance of y comma x is same, minus 331.8. And then the covariance of yy is 18770. So now it's a time to take a pause and think about these numbers. So if you see here, covariance of x comma x 6.63697. What, and if you see here covariance of y comma y 18770. So what does that means? It tells something about the variance or the spread in the data. If this number is small, that means these numbers are closer to each other, isn't it? Yeah, so ranging from 0.9 to 5.8. There is no big spread in the data. So that's why you see a small number here, covariance of x comma x. Whereas you see the y value, it has a bigger spread starting from 35 and it ends at 250, isn't it? Yeah, so that's why the spread is really huge. And that's why you see the covariance of y comma y is such a big number when you compare to covariance of x comma x. And another noteworthy thing is you see some negative number here out of nowhere with respect to covariance of x comma y. So what does that mean? Which means there is an opposite trend. You know? In other words, if this value increase, this value decrease. If this value decrease, this value increase. So you can see the trend already here. You know? So let's say x 5.8 and here 0.9. When x value, which is decreasing, on the other hand, your y value increased from 35 to 250, isn't it? Yeah. So that's why you see a negative number. There is an opposite correlation. Yeah. And then again, this number, the magnitude 331. So if this increase, this one decrease. If this decrease, this one increase. And if the observed change in increasing or decreasing in the y value, if it's not huge, if it's not really huge, then even this number will be smaller. Yeah? So 331.88, that means this means there is already a significant change. A small change in x will cause a big change in y, and the change will be in the opposite direction. So that's the meaning of this number. So your covariance matrix already have some information. Yeah? And one more thing, so it carries some information about your x alone, it carries some information about your y alone, and then it carries some information between x and y. If x increases, what happens to y? And it also have some information about covariance of y comma x, which is y and x. If y changes, what will happen to the change in x? So what we did is we captured the spread in data amongst the variables, and then with respect to each other, all the variables involved, ordered pair of variables, all into one single matrix, isn't it? Yeah? So what S means? S help us to carry all the information in the entire data set into a 2 by 2 matrix. So that's what I want to emphasize now. So in the process of deploying PCA, we try to calculate the covariance matrix. That covariance matrix already have some information about all the variables and how they change with respect to each other and with respect among themselves. Yeah? So the variance in x and the variance in the y, and the covariance between x and y, and the covariance between y and x. So we carried a lot of information, and then we converted that information into a mathematical format, which is nothing but your covariance matrix. So keep this thing in mind. We completed step 1 of PCA algorithm. We have to do a few more things. Yeah. So still we need to find, if you remember in the very first video or second video, I mentioned about we have to find this optimum eigenvector, or something called as the principal component. So that's where we will do that now. Yeah. So to do that, we need the covariance matrix. Covariance matrix. Yeah. So let's see. So we need the we already have the covariance matrix. Now we have to do the next step. The step 2. So the step 2 in PCA, so the step 2 in PCA is to get the so step 2 in the PCA is to compute something called as the eigenvalues. Eigenvalues. So eigenvalues will tell something about how much information that we can capture in each component. So if I remember, I said you have two variables. So two variables, which mean you can get two components. Yeah. So I will quickly revise what I said in the previous videos. If you have two data, something like that, I mean you have x and y. So you can draw one component like that, and then you can project here, and then everything will overlap. Yeah. So which mean in the variance of the data, variance among the data in this line, or this something we can call it as vector, or we can call it eigenvector or principal component, is very low. And imagine if you have another vector which is something perpendicular to this one, and if you project all these data points, you will have a clear separation. So in this case, that means, and clear separation in the sense you are observing a clear separation because there is a big spread in the data, which means the variance of the projected data in this component or in this eigenvector, follow the pen, in this eigenvector will be higher. And we have to compute, so what could be the variance? So how much of information is captured on this line and how much of the information is captured on this line. To get that one, some information about that, like a percentage of information captured in this eigenvector are also called as principal component. Another eigenvector are called as the another principal component. That to do that, we have to calculate the eigenvalues. Okay, so eigenvalues is something, if you want, although it's not the right word, to just for you to remember, we can call information, a value that tells something about the percentage of the information that we can capture on the PCs. PCs are the eigenvectors or the principal components. Okay. So how to do that? The formula is very simple. So determinant of S minus lambda I is equal to 0. So lambda is nothing but your eigenvalue, which is here. So if you have two, so if we go back to the data, so if you go back to the data, you have two variables. So you have two variables, which means it's a 2 by 2 matrix. Which means you have two variables. Sorry, I forgot the number of columns. If you have two variables, which means you can make two principal components, which means you need to calculate two eigenvalues. Yeah. So which means one component will carry some information about the entire data set. The other component will carry the remaining information in the entire data set. And if you sum these two of the information captured in one component and in the other component, that makes the 100% of the information. Yeah. So which mean you will get one lambda for this component, and then you will get another lambda for this component. So is safe. So the lambda for this component says 99%, and the lambda for this component is say 1%. The total should be 100%, which means the total variance will be 100. So if you have two components, that will capture 100% of the information in the data, but only one component may be enough to capture the 99% of the information in the entire data set, both x and y. Okay, so let's do this s minus lambda I, which means you need two components. So I mean since you have two variables, you will get two lambda. You will get lambda 1 and lambda 2. Okay, and typically the lambda 1 is the tells about the percentage info captured or the percentage variance in the first principal component. First principal component almost carry the majority of the information, and then lambda 2 is the percentage information of or variance captured in the remaining PC. In this case is the second PC, second principal component. Yeah, so remember these things in mind. So this is a very tricky algorithm. So you must watch this video fully. Don't skip any part. Try to watch everything, only then you can understand this algorithm. So it's like 2 hours of investment, but you know everything about this algorithm. Actually, I made this explanation really simple so that anybody can understand, even though if you don't have a good mathematics, I mean good background with mathematics, still you can understand. I purposely made the concept simple. So let's say calculate the determinant. Our S value is what? S is covariance matrix. So just now we calculated is so 6 minus 3697 minus 33 1.8 minus 33 1.8 18770 minus lambda into I is nothing but identity matrix, so which means the diagonal element will be 1, and the size of the identity matrix will be equal to the size of the covariance matrix. Your covariance matrix is 2 rows 2 columns, which is 2 by 2, and then the size of your identity matrix will be 2 by 2. So you multiply that by lambda, so that should give lambda multiplied by 1, lambda multiplied by 0, lambda multiplied by 0, lambda multiplied by 1. So lambda I should be equal to lambda 0 0 lambda. So the determinant of S minus lambda I should be equal to 6.3697 minus 331.8 minus 331.8 18770 minus lambda I is this one, lambda 0 0 lambda. Just subtract this matrix from here. Yeah, so if you don't know how to do the matrix subtraction, just follow the procedure whatever I'm going to do now. So 6.3697 minus lambda minus 331.8 minus 0 here, and here minus 331.8, this element minus 0, and then here 18770 minus lambda. So this is nothing but S minus lambda I. So this is equal to 6.3697 minus lambda, and then minus 331.8, and then here minus 331.8, sorry, 18770 minus lambda. So this is nothing but S minus lambda I. So now we have to calculate the determinant of this number, so which is determinant of 6.3697 minus lambda minus 33 1.8 minus 33 1.8 here 18770 minus lambda, which is equal to 0. So this is the method to calculate the eigenvalues. Determinant of s minus lambda I, that should be equal to 0. That should allow you to calculate the eigenvalues. So if you have 2 by 2 matrix here, you will get 2 eigenvalues. If you have 3 by 3 matrix here, you will get 3 eigenvalues. So let's calculate this one. So how do you calculate the, how to get the determinant of this number? So how do you do that?